Igor, you're sharing, right?
I am sharing. Let me share.
So Igor's going. We're going to tag team. I start, then Igor takes over when it gets technical, and then I finish. This is about spinning up a virtual world-class supercomputer. So what we actually did, the punchline basically of what you're going to see is that Saturday morning before Supercomputing 2019, we bought all the GPU capacity that was for sale in Amazon Web Services, Microsoft Azure, and Google Cloud Platform worldwide, right? And you will literally see that we bought everything worldwide. We created thus the largest cloud simulation in history, according to the NVIDIA CEO. In this is 2-hour simulation, or 2-hour experiment, as I like to call it, we bought 51,000 NVIDIA GPUs in the cloud, which sum up to about 380 petaflops 32 for 2 hours. And it was distributed across the world. And we used multiple NVIDIA generations, basically everything that could be bought. We were maximally promiscuous. And next slide, Igor. Now, how did we get there? How could we be so brazen and do something like this? The reasoning is that we had an application ready to go. We had several years worth of experience working with these people. And the structure of what we do for them is no different than running this in the cloud. The big difference is the scale. And so typically what you see here is a timeline of the number of GPUs that we normally run. So this is peaks at about 3,500 GPUs for a day. And this is the time period is the last year. And the different colors are different locations in the world where those GPUs are physically located. So normally we run an on-prem infrastructure that is global. And for this 2 hours on that Saturday, we ran an in-cloud infrastructure that is global. So all of the infrastructure stuff, the how to make this work was identical to good approximation. And the application is the same. So that's why we could possibly imagine doing such an outrageous thing. Next slide. I want to start by explaining you a little bit what the science is. The IceCube experiment is called IceCube because it is literally located in a 1 kilometer cube of ice in the Antarctic. So what you're seeing here is, in fact, it's literally located right smack at the South Pole. What you're seeing here is a schematic of how this works. The y-axis is the depth into the ice. So down here, by the way, you can't see my cursor, right? So only Igor's cursor can be seen. Okay, fine. So Igor, you have to imagine, you have to follow while I talk with somehow moving the cursor. So down here at a depth of 1,450 meters to 2,450 meters, they have modules lowered into the ice. So you can imagine lowering a string through a hole in the ice that you heat up so to unfreeze the ice. And then when it becomes water, you just lower the stuff in, the equipment in. And the string has it also functions, gives stability, and it has the cables that go to the top. And down there, you have multiple optical modules. They're basically they're light detectors. And voila, you detect neutrinos that create muons in the ice or electrons in the ice, and you reconstruct the trajectories. That's basically what it's about. And this facility is for many different kinds of science. We focus here on astrophysics, and the rationale behind doing this is described in this plot. What's plotted here is the energy on the x-axis and the distance in megaparsec, an astronomical unit, in the y-axis. And this black piece here that says terra incognita is the range where light does not travel through space. basically, when you have light photons high enough in energy and far enough away, they will not reach us. And so stuff that happens in the universe that is in this sort of energy range and distance can only be seen by neutrinos or by gravitational waves. And so the neutrino detector astrophysics program is literally built to see the stuff in the black region. Now on the right here is a plot that shows, again, on the x-axis the energy of the photons, sorry, the neutrinos, and on the y-axis it shows the rate at which they impinge on the Earth. And what you see here is, in blue, you see the stuff that comes from our atom, and in red you see the stuff that comes, or from the sun. In red you see the stuff that comes extra outside the solar system. And so what you can see here is that cleanly the high energy neutrinos are not coming locally, they only come from far away. And it's these high energy neutrinos that we're focusing on. Next slide. Here is an actual publication, an actual plot out of a publication. The publication that at IceCube is famous for establishing that this is actually for real. What you see in red is photons from from the Fermi satellite, and you can see that photons above a certain energy of about a TeV no longer are visible. They basically don't get to the to Earth, whereas the neutrinos still exist and exist at higher energies, and that this one picture both establishes that the photon that the universe is opaque to photons, and it establishes that neutrinos, it is not opaque to neutrinos, and that actually violent interactions in the universe exist that send us very high energy neutrinos. So this demonstrates both of these points. Next slide. Now, the name of the game, now that we have established that these things exist, the name of the game is to understand where they come from. What's the physics? What's the science behind this? And the objective here is that these most violent, the hypothesis is that these most violent events in the universe that give us these high energy neutrinos also give us photons, and they give us a whole spectrum in energy of photons. And so we can use the neutrinos to establish that something was violent, and then we can look at the spectrum of photons in order to understand the dynamics and the process characteristics. And therefore, by correlating measurements with photons with measurements with neutrinos, we can understand the science. And the buzzword for this is multimaster astrophysics. This is one of the 10 grand ideas of the NSF, grand challenges or foci of the NSF that it puts a lot of money into. And so what we're doing here, using as an application, is directly high on the hit list for the NSF. Next slide. And so this is sort of a slide of a couple of slides to show you how this works. On the right is an actual picture to show you the color of the light that is being detected. And on the left is a reconstruction. The little dots here that you see are the measurements of individual photons in the various tubes. The size of a ring gives you the energy. A size and color gives you the energy. And then you can sort of see that the reconstructed neutrino direction from this blob of measurements. And it gives you a little bit of a sense that there is an inverse problem here of figuring out where the neutrino came from given what you see. And that's what I'm going to talk about next. Next slide. And that's ultimately why we need GPUs. So this slide describes the neutrino detection challenge. In other words, the inverse problem of seeing light and knowing where the neutrino came from. And ultimately what we have done is we've simulated photon propagation through ice, because that runs very efficiently on single precision GPUs. And as input data, we have taken a Fortran simulation of the neutrino hitting the ice, creating muons, creating photons, and the photons are then stored and put into the simulation of the GPUs as input data. The GPUs simulate the photon propagation outcomes, data that then can be used to understand the detector characteristics, to basically characterize the detector. And given that this is in the South Pole ice, characterizing the detector really means not just the instruments that are deposited, but also the ice itself. And so let me walk you through some of this here. On the top left is a deposited energy, again on the x-axis, and on the y-axis is the median angular error. So in other words, every one of these dots is a measurement, and it's a measurement of an energy and an angular resolution. And the red line is the theoretical precision obtainable if we had perfect understanding of the ice. And what you can see is that these measurements have lousy precisions compared with the theoretical achievable. And that is one of the challenges that we're trying to solve here via photon propagation through ice. Basically, by improving the model of the ice, what the ice is like, we get rid of the systematic error here, implicit by the blue points being higher than the red curve. A specific example is in the bottom left. This is the error ellipses of one event for different reconstructions. So you can see that it moves around all over the place. And it moves around systematically in ways, and the only difference between these is basically difference in the reconstruction, the ice model, and some other features. And on the top right here, it shows why this is complicated. What you see here is a three-dimensional plot of wavelength, depth in meter in the ice, and scattering coefficient. It is essentially the y-axis is effectively the quality criteria of the ice. How much scattering do you have in the ice as a function of depth in the detector and a function of wavelength of the light? And you can see it goes all over the map. And that's just because the ice has grown naturally because we didn't make it. It was made by nature. And having an understanding of this is what ultimately influences going from achieving better resolution. And the bottom right is the kind of improvements that that are expected, hypothesized to be achievable, given better improvements in the reconstruction with better ice models, etc. In addition to better ice models, there's also improved E and tau reconstruction. I'm not going to get into this. Basically, you can multiply the reconstruction efficiency by something like a factor 2 to 3 by getting better reconstruction. Next slide. So this is the reason why we do this. And now, so what's the, so that was the technical reason. Now, a first evidence that this science is actually doing something. There is so far one time in history has a neutrino been observed by IceCube, and then immediately the world has been alerted to this, and telescopes the world over and in space have turned in the direction where IceCube said, look there. And then they discovered that in fact there was photon activity out of that direction where the neutrino came. And this was a huge splash in the scientific world and was published in Science in this article. And so we have done this once, or they have done this once, and they want to do this many times over to actually really understand where these high energy, most violent events come from in the universe. Next slide. And this is not just something that is a one-off. IceCube actually has been running for 10 years and is expected to run. They have an upgrade plan for another 10, 15 years or so. And then they're expecting to run for another 10 years. So we're talking about an experimental program that is going to probably last well beyond when I retire, meaning into the 2040s before it's done. And what you see here in the schematics is the timeline of the wished for upgrades or the planned upgrades. And what you see in the bottom is this orange cube is the current instrumented detector. The green ones is much more densely instrumentation that they're putting in place soon. And then this sort of extra area is a future extension of the array. So they're planning to make this detector a lot bigger. And then they are going to put on top of the ICE radio arrays. So there is a large number of upgrades over the next 10, 15 years in order to improve the instrument. And all of this will continue to need simulations of the type that we've just done. Next slide. Now I think, Igor, are we switching now or a little later?
Yeah, that's mine.
Okay, so now Igor takes over and talks about the technical aspects.
Right, so Frank did a good job of showing why we need this and what the science is all about. I'll go more down to earth and explain what we did in more technical details for this particular exercise or experiment, like Frank likes to call it, and which gives you a different point of view of what was done. So Frank already mentioned it in the beginning, but let's recap. The basic idea of what we did was to integrate all the GPUs that were available for rent worldwide in a single resource pool. And we wanted to do it with through the three major providers, which happened to be AWS, Azure, and Google Cloud. Although we tried Oracle a little bit, but not at these scales. And we wanted to really use all the GPUs anywhere. So we had to go wide. We had to get the GPUs from about 30 regions from all over the place. And one of the challenges was we didn't really know how much we will get because we asked around, including the cloud providers, and they said, oh, I don't know, this is the range, which was like an order of magnitude one. So we had to really hedge our bets and try to understand how much it will be and would it be worth it, and what if we get too much, we'll be able to manage it. But the hope was that we would get at least something that will be in the range of the larger HPC system currently deployed, so it would actually be useful. And one of the reasons for doing this is because, as you all know, there is this big push for Exascale coming up. And we wanted to use this clause exercise as an also as an exercise to prove that we can actually do stuff at these large scales. Getting a whole big HPC system, it's actually not easy. They are deployed, but it's really hard to get access to a whole one. So we said, let's see if we can do something like that using the cloud. Before we show you what we actually managed to do, again, something that Frank mentioned, but let's make it clear. IceCube is an open science grid user. So it has been doing distributed high throughput computing for a while. We also like to call it ingenious HPC because it takes a little bit of thinking in order to partition your problem in such a way that there are very few, if any, dependencies between jobs. Some problems are easier, and IceCube is definitely easier than, say, Fusion, which I would love to be able to decompose it that way, but it's probably impossible. But you still need to think carefully in order to do it. And essentially, you get a lot of independent tasks, and then you can schedule them very easily through something like HT Condor, which is a resource orchestration that can combine any kind of resources together into a single pool. And HT Condor is already used in Open Science Grid, so we use the same one, and added cloud resources was not really that much different than adding OSG resources. And Frank already showed that we already are used to run all over the world. So here is what we got. We got about 51,000 GPUs, or about 380 22-bit petaflops. Here you see all the regions we got them from. Unfortunately, I cannot tell you which cloud providers provided what. We're not allowed to say that. But you can see that there are a lot of stripes. Some provide more, some provide less. but none of them provide the majority of resources. So if you want to climb this high, you really need most of these stripes. You may probably get rid of some of the really thin ones, but that would still not get us as high as we got. And you can see here on the right side that the resources really came from all over the place. The US is a big player, but you still need Europe and Asia Pacific if you want to go really high. So it's really important to be able to go all over the place, and unless you have very few dependencies between jobs, that becomes a really, really hard problem to tackle. Luckily, you worked around that a long time ago by being a OSG user. We also went wide on the GPUs because cloud providers have a lot of GPUs, but not a lot of GPUs of a single kind. As you can see here, here is the number of GPUs, and here is the petaflops. And of course, the newer GPUs are more powerful. But you can see here too that in both things, apart from this tiny red light, which is the P4s, which are really not that prominent in the clouds, we needed all of them to get this high. If you take any slice out of it, you lose quite a bit. So if you want to get really high, you need to be able to use anything that they throw your way. And IceCube is using OpenCL as their programming model, and that it's very, very easy to run on pretty much any GPU with just a little bit parameterization to deal with a different number of compute units that the various GPUs have and amount of memory, but that's about it. Everything else just comes for free thanks to the runtime. So single executable, you don't need to rebuild everything for every possible GPU that you may put your hands on. And here is just to get comparison to what you can do on-prem. If you wanted to go to a single system, the biggest one currently deployed is Summit with its 21,000 something V100s, and that gets you to 400 petaflops, which is a lot, being a single system. But if you don't care too much of having everything collocated, you can actually get pretty close in the cloud. We got to 380, and I'm pretty sure we could go to 400 if we really pushed. We had about 2-hour time limit to ramp up, and we stopped there. So yes, you need machines like Summit when you have tightly coupled jobs like Fusion. But for distributed high throughput computing jobs, cost apart, the cloud can provide you a system that is just as big, and all you need is money. And let me stress that we really had no special arrangements with the cloud providers. We just picked a time and started requesting. So there were no reservations, no long time commitments. It was just, let's do it. Now, said that, they're setting up the accounts and get all the quotas raised was not trivial. When you set up an account, by default, you get very low quotas. And I believe it's mostly because they don't want you to rake up a multi-million-dollar bill that you cannot pay. So it takes a little bit of social hurdle to get them to agree or to raise those quotas. But you have to go through this process once. And just so it's clear, raising a quota doesn't guarantee that they will deliver. We had quotas that were way bigger than what we actually were managed to do. It's just a limit of what you're allowed to try, and it's practically just financial protection for the cloud providers. So that was done with ran. We just used the straight cloud APIs, no third-party cloud provisioning tools for various reasons, but the major one was cloud APIs are just so damn simple to use. So why use anything else, especially when you do a one-off experiment that is pushing the limits. and it was not hard at all. All you have to do after you got all those VMs starting is glue them together. And as I said, HT Condor that we usually use in OpenSense Grid does a great job. So it was really like gluing together all the OSG resources that we already have. So we used a dedicated hardware setup just because of the size, which was about 20 times bigger than what IceCube usually runs into. So you can imagine that you need a little more hardware to deal with it. But the software was the same and the configuration was almost identical. Here I have another point of view of the cloudburst, and this time from the science point of view. The other one was just what you see, the number of GPUs provisioned. Here you see how many simulations were done for the different regions at the end of the run. And you see, again, they came from all over the place. Again, cannot tell you which cloud providers provided which, not allowed. But you can see that the largest region, which is either this or this, was only about 10% of the total. So if you want to get to those big simulations, you really need to go pretty much anywhere. And distributed high throughput computing is definitely the way. Here I have another slide that shows you the fact that we can use different GPUs helps. I will not show you the distribution, you see it before, but I wanted to stress that different GPUs really provide different runtimes. And for some older GPUs, it was so long that we decided, let's just run smaller jobs there, because we had a deadline of 2 hours, and on the K520s, it would take 5 hours to complete our jobs, which was definitely too long. And especially if you want to use preemptible resources, you want to run short. So there was a little bit of work done, but not that much. And you definitely don't want to run too many jobs, because that puts high stress on the provisioning system. And here you have a plot that it's a result of the previous distribution. The older GPUs accounted for 50% of the runtimes, but less than a quarter of the time. So you see, this is the runtime, and about half of the time was the old GPUs, but they provide very little in terms of scientific output, while the newer GPUs provided very little runtime, but a lot of output. So newer GPUs are definitely more effective, both because they are faster per se in theoretical flops, and because they are way more effective in terms of runtimes compared to their theoretical flops. This also has huge implications on how cost effective they are. And you see that the T4s, which are 32-bit optimized, they are not very fast, but they cost really little. So when you see how much you pay for a single job, it's about 10 cents per job. Teslas are very, very fast, but they are also very, very expensive. So they cost about 3 times as much per job. And if you go with the really old ones, they're cheap, but they're really slow. So at the end of the day, they are about 10 times more expensive per job than Tesla T4 is. So when you have the luxury of actually go and pick, and you are not just looking go and choose, and are not just aiming from the maximum possible like you would do, picking the right GPU can make a huge difference how much you pay. And this gets us to what we did afterwards. So that was the first run, and where we really wanted to see how much was available, but it was an experiment. We wanted to know how much we can get, and how much we and what was actually available, but that's not what you would normally do in real life. In real life, you are not interested in peak. You want to do something that is maintainable at a reasonable time, at a reasonable price. And that's not what we did in the first place, because that was not the objective. So in the second one, we wanted to read data straight from the on-prem storage. We pre-staged all the data into cloud storage in the first run because we didn't want to worry about that. We extend the time frame, not just a short peak, but let's try to do it for the whole workday, because if you do it for something real, just ramping up and ramping down fast, it's not what you would typically do. Let's not be too picky about the date. Last time we picked a Saturday because we said that's likely when most of the resources are available, but most people want to work on Saturday. So let's just do it in the middle of the week. And let's be a little cost conscious. As I said before, there is a huge difference in cost between the cheapest and the most expensive GPU. If you do it as an experiment to reach the peak, you throw money at it. Whatever it costs, it costs. We don't care. We really just want to see what's available. If you do it for several times for production quality run, you probably care about the cost. So we decided, okay, let's just limit ourselves to the 3 most cost-effective GPUs that we are aware of, which are the T4, V100s, and P40 at that point in time. And let's just use preemptible or spot instances because they cost about a third of the on-prem. We said, given our previous experience, we should be still able to get to about 100 petaflops, which is huge. Not as huge as before, but still it would be, I think, a number 3 HPC system on the top 100 for DHCC, of course. We did it, and we actually got way more than we were hoping for. We did it on a Tuesday in February, ran 9 to 5 PST, and with 6 hours on up here on more or less steady state, plus about an hour out, an hour down to minimize the loss. And it was about 15,000 GPUs, about 170 petaflops. And these 6+ hours integrated about an exaflop worth of GPU compute. So we got a lot out of it. And this was all using just the 3 most cost-effective GPUs and all in preemptible. The cost was approximately $60,000. Not exactly. We are not allowed to tell you the exact number, but take it with the plus minus 10% error range. And this includes everything. Includes all the storage that we used. We still sent the outputs to the output storage, to the cloud storage for various reasons, and all the networking that was involved. Now, $60,000 is not exactly cheap, but for 1 petaflop, it's not that much. Consider that something like Summit costs tens of millions of dollars to build. Yes, it's used for a long time, but unless you have a really big need, you will not be able to get on it at these scales. Now, we used only preemptible or spot instances to get to this price. So there was some loss, but here I have the difference between how much we provisioned and how many jobs were completed. So the difference is basically what the preemption took away. And you see it's not that big. It's about 10%. So we wasted about 10% of the time we paid in the cloud to save about 66%. I would call this a really great deal. So definitely we plan to use preemptible resources in the future too. And it was pretty straightforward. We learned a lot from the first round, so the second round was pretty straightforward. I spent some time looking at the graphs just to make sure that we could keep as high as we could for the resources we have available. But if we were happy to stay at 100 petaflops, I probably could have just turned it on and forgot about it. We are confident we can do this anytime. The only really available limit is the money. We currently don't have money to do many more of this, but it was pretty straightforward. And here I turn back to Frank, who can provide, again, a big picture view of what we did.
Okay, next slide. So we want to talk a little bit more about total cost of ownership, so to speak, issues. The burst was executed by two people, Igor and David Schultz. Igor supported the infrastructure. David supported the actual workflow and ran the job, so to speak. So a David type person would be needed even if you had on-prem. So when I'm analyzing cost, really, I have to assume that I would have to hire an Igor type person or pay Igor's salary to make something like this happen. And in addition, if we want to make this a routine operations capability for many customers, then in science or industry for that matter, I think we would in addition require at least a 50% FTE cloud budget manager. That 50% FTE would be a function, would sort of linearly grow at some level with the number of customers, because there's substantial effort involved in just dealing with costs and budgets for large community of scientists. Strangely enough, buying cloud capacity and paying for it is not effort-free. It's actually highly complex and involved. And we have lots of funny stories to tell about that over beer, so to speak. Next slides. So to provide an aggregate exaflop 32 hour per day of DHCC production capability in the commercial cloud for the sum of many sciences today would require about this kind of effort. You'd spend about $60,000 worth of buying cloud purchases, and then you'd have to pay salary for 1.5 FTEs of human effort. And you'd have to, of course, hire the right people. Igor always loves to say, this is easy, this is trivial. It is easy and it is trivial for if you have the right personnel. This does not include the effort to train your application community to define the workflows, run the workflows. And it does not include what the scientists themselves still have to do. In other words, the David Schultz type people are not included in that cost. So a business venture who wouldn't want to make money, just want to break even and do this for all of open science in just the HTC kind of capability would be structured like this. Next slide. Now, how applicable is this to things other than IceCube? In my mind, all the large instruments we know of do this kind of computing, whether it's the Large Hadron Collider or LIGO or DUNE, LSST. You pick a large scientific instrument, you are almost guaranteed that they do this kind of computing. It sort of lies in the nature of the beast. Any mid-scale instrument we can think of is also similar. And that includes both the instruments in physics and astronomy, but it also includes cryo-EM. All of the cryo-EM instruments that are now being deployed all over campuses nationwide and a research institution that do structural biology, the core, the ones at UCSD that we have, the core reconstruction software is ported, runs on GPUs, and it runs on it even runs primarily on 32-bit. Then a large fraction of the machine learning community would be able to work this way because they train or do inferences on such single GPUs rather than an multi-GPU infrastructure. So basically, it's not all of deep learning. There are some deep learning projects which have fundamentally MPI applications because they have very large memory footprint. But the majority of deep learning applications that you see are not tightly coupled. And so in essence, any kind of application that has bundles of independently scheduled jobs that can be partitioned to just workloads to have half to few hour runtimes on modern GPUs work that way. And this being able to or design the input data in such a way that the job doesn't run too long is actually crucial. I mean, and Igor said that the losses due to preemption were 10%. This is, of course, directly related to the fact that our runtime was only between 20 minutes and an hour or so. If you cannot make reasonable runtimes, then you cannot use preemption. If you were to run 3 days or 5 days, you would never run to completion much less as often. And so this is an important design criteria when you're trying to run like this. Next slide. This, in closing, I want to even zoom out even further. These enormous instruments, unique instruments globally, like IceCube, are sort of special in that humanity has built these extraordinary instruments by pooling human resources and financial resources globally. They pose large compute challenges that can also be overcome by pooling resources from major data centers, both on-prem and in the cloud. And using the DHCC paradigm is sort of the obvious way to deal with this, because it is fundamentally designed to allow pooling, and therefore it is designed to be the right tool for global cooperation of large entities. And that's it. Thank you. Questions?
Thank you, Frank and Igor. That was really interesting. So we are going to turn off the recording now and take the rest of the time for Q&A. So I think you're able to, for folks who have questions, I think you're able to unmute yourself and ask the question yourself, or you are welcome to type it into chat and I will repeat it.